Hi everyone. So today we're going to be talking about introduction to bit hacks, and the reason why this exists is because I already given a lecture about called Fun with Bit Hacks, and the feedback that I got from it is that while like the first couple of minutes the examples are easy to follow, then they quickly transition into these very hardcore and hard to follow bit manipulations. While the performance gains are cool, it's very hard to follow and even harder to implement yourself. So there's no actually explanation how they work. And this video is actually here to fill this gap and to actually give you a proper introduction to bit hacks. Um, it's in C#.net, but that's not really true because you can apply this knowledge to almost every language. It's just that some of the examples are gonna be in C#.net, but most of them actually won't because we're gonna actually do just expressions. So let's jump in. So why would you like to ever want to apply them? So it's branch elimination and batch computation, and this actually boils down to better performance and better memory utilization. Then we have compact data representation and simplicity. So we can actually use implement our like bit sets that actually can be like a very compact data structure. So for example, if you have a big data set somewhere lying somewhere on disk because it's so huge it cannot actually fit in memory, you can have a bit mask that actually says if the value is, for example, set or is this record present in the database. And of course, simplicity. You can actually have certain, like, again, masks and data structures that actually make your code more simple. Okay, so let's jump in. And I've written this interesting bit of software that actually allows us to visualize these bit manipulations better. And it's actually from another project where this is like a language and a compiler backend, but that's not really important right now. What's important is that I've taken just a small chunk of that project and implemented this visualizer. So how does it do the stuff? Well, if we say that we have a number 1, it's going to represent it in binary using signed int32s. So I can do stuff like that, and it's going to tell me how it arrived at the result that it arrived. Okay, so now let's clear the screen and let's start with something very simple. So for example, if we have value like 0, we can treat it this as a bit mask, and we can do all sorts of things with it. So let's implement a data structure called a bit set. It's going to be a very simple bit set, but each bit set has to have a bunch of functionality. So for example, first of all, we would like to know how to set a very specific bit at a very specific index. So how would we set a bit on like a desired index? So let's just call it a mask, and our mask is going to be 0 now. Let's do a OR operation, and let's have a value 1 shifted by our index. And our mask is 0. Let's just say it's going to be an index 4. And what actually happens here? So we take our single bit, we shift it 4 times, so it's shifted here. And now we're going to do a OR operation with an empty bit mask. And OR is more like merge, so whatever you have a bit set, it's just going to merge these two at each side. So we're going to arrive at this specific bit set in the correct position. Okay, so now that we have this first method implemented, we would like to know possibly if a bit is set in the mask. So how do we do that? Well, we have to change a single thing. We have to change the OR to an AND operation. And hopefully you know why, but let me do some explanation. So this is all the same. So we actually are here now. So we have our like bit set here, and we're gonna do an AND operation, which actually will it will only work if you have ones on each side, right? So in this case, it's gonna work. But if we were, say, interested in an index that's not actually set, then it's gonna end up at 0. And you might have noticed something here. So if the bit is set, we're actually having a value. But if it's not set, we're going to have 0. Depends on, well, is it an issue? It depends on what your business application is for the problem. But if you're interested in like a 0, 1, or perhaps a Boolean value, we can actually change this up and say that this whole thing, if it's something else than 0, then the bit is set. If it's 0, then it's not set. So if it's 2, it's not set. And if it's 4, well, it's set. So now we have this pretty good representation that we, for example, want to end it up with, because when we're doing branch elimination, we're actually very interested in these like flags, and 0, 1 is actually useful. And maybe let's actually talk about branch elimination, because every time I'm talking about branch elimination, I'm actually talking about eliminating if statements in hot code paths. So if you have like a for loop and it's doing some computation, then you're interested in eliminating an if there's if you have an if statement there. And it's because there's this thing called a branch predictor, which will actually put instructions in the CPO pipeline ahead of time, but it will guess if that statement is actually correct, if that branch is actually predicted correctly, and if it's gonna miss, then you're gonna have a very big performance impact and you're gonna stall the pipeline. So it would be better to not actually have any predictions like that, because if we know that we can eliminate branches, then that's good. So okay, now we have, like I said, we have either a 1 or a 0. That's really good, but that's not really good because this in different compilers is gonna behave differently, but in C# at least, this is gonna return true or false, and it's not an int, it's a boolean. And what's the problem with that? Well, the problem is that you cannot do a lot with booleans. You cannot do branch elimination with booleans because you have to convert them to a number. And this is possible, of course, but it's not free, and you're likely to have if statements there as well. So that's not really cool. And depending on the compiler that you're going to use, this can be actually turned into an if statement as well internally. It's not going to happen on like a .NET Core compiler, because it's going to set that boolean correctly without issuing any like jumps and stuff like that. But there are like different compilers, so you might have problems as well here. So how do we solve this problem to actually have a number, not a boolean value? What we can do here instead is we can shift back by the index. And now, if we're going to have the value 4, which is saying that it's set, we're going to have 1 here. And if we're going to have something else, like let's say an unset value, we're going to have 0. So, and this works because if something is set, it's going to be 1 at that at that position, and we can shift back by that position, and that's it. That's mostly it. Okay, so this actually solves the problem. It's a bit slower than just using like not equal 0, but at least we're gonna end up with integers, so we can actually get that performance hit back at a later stage, for example. Okay, so now we know how to set the bit, we know how to check the bit. So let's implement a function that actually unsets the bits once it's set. So how do we do that? Well, if we were gonna shift by that index, now what we have to do is we have to negate. So everywhere where you have 0, we have to have a 1 in order to not delete the bits that we don't want to delete. And we're going to have 0 at this position, and if the bit is set, we're going to have 0 and 1, and it's going to end up in 0. So that's good. That's what we want. Again, let's do 16 for... I need to negate first. Sorry. 16 for unset correctly. Okay, that's good. That's very good. So what else? What else could we want with a bit set? Well, we could actually say that maybe it's going to be useful to implement a function called toggle. So if a bit is set, we're going to unset it, and if it's unset, we're going to set it. And we could do that by doing an exclusive OR. As you can see, it did unset the bit, and if we're going to do index 2, it's going to set the bit. So exclusive OR will actually, well, so exclusive OR will actually set the value 1 where there's 0 and 1. And if I remember correctly, because I might be wrong by that, I might be wrong, where you have 0 and 0, it's just going to say 0, and if you have 1 and 1, it's just going to say 1. Let's verify. Okay, so and if you have 0 and 0, it's going to say 0, and if you have 0 and 1, it's going to say 1. 1 and 1 is 0. Okay, yeah, I had to recall that. All right. So now that we implemented all of these forum methods, we actually have all of the building blocks to be able to implement a bit set. So let's maybe implement the bit set in C#. And I have already one implemented. So as you can see, this is a very simple data structure. It has some extras here because we want to be able to represent more than just 32 bits. So we have an array here, and we're just going to have two methods now. So we're going to have add. As you can see, it's doing the OR, and we're going to have the contains, which checks if it's set. We could add toggle and others as well, but for this implementation, it's not that important. I just wanted to show you that we can actually implement a bit set now. Okay, so going back to the examples, let's actually implement some of the bit hacks that actually are going to be useful for branch elimination, because the things that we did now aren't really to eliminate branches most of the time. They are actually used to implement a data structure called a bit set. So let's start with something simple. Let's do a function called negate, and it's gonna be an unconditional negate. So we're gonna do value x or minus 1 plus 1. Let's go with value 4. Obviously, we did a negation, and every number x or minus 1 it's just gonna change the sign and increase it by 1, and then to actually decrease that number again, we're gonna have to add plus 1. So it's correctly negated. Let's actually test it with a minus 4. So we arrived at 4 correctly. So minus something x or minus 1 is actually now decreasing the value by 1, not increasing, and again changing the sign. So now we're gonna add, and we're gonna end up at 4. Okay. This negation is actually really useless because you can do just minus 1, minus 4, minus 3, minus whatever, right? So it has some niche value it can be used in like certain instances, but most of the time you're just gonna be slower and you just have to use minus some value. So why did we even implement that? Because that's silly, right? Okay, we actually implemented that because now we're gonna take this and we're gonna implement a conditional negate, which is not something that you can do easily without bit hacks, and this can be used to like do branch manipulation, because now we have a condition, and that condition is a simple like 0, 1 flag. So let's actually do that. So we're gonna have a new thing here called a flag. So let's do negate again. Let's have this value flag. We're gonna XOR as we used to, but now we're gonna have flag -1. And instead of like adding 1, because that's useless now, we're gonna multiply that by the value. And our flag, we have to provide the flag. Let's provide 1 for now, and let's go with 4. So we have 4. So 1 actually means don't negate, don't do anything. And when we run it again, but the flag will be set to 0. Again, let's do 4. We're gonna negate. And the reason it actually works is this first part. So this is our this is actually called a conditional flag. We can apply this to different bit expressions, because this actually makes this sort of bit work, because it's going to end up either or 1 or -1. So we're going to end up at -1 here, because what we're going to do is we're going to XOR in this example with -1. So that's going to change the sign, and by changing the sign, we're going to multiply by -1. And if we have 1 here, that's going to be 0, so that's not going to change the sign, and we're just going to leave this value alone, and that's it. So that's it. That actually is useful to do branch elimination. Okay. Let's move to some other examples, the simple ones. Let's compute the sign. So every time you want to compute a sign, like we have to shift by 31 in this example, and let's do -4 shift 31, and our results are 0 or -1. So we know how to compute the sign, but we perhaps would like to know why we're using this magic number called 31. So we arrive at this number by taking the size of a int, which is 4 bytes, multiplying that by the number of bits in a byte, which is 8, and that's going to give us 32. And since these are signed integers, we actually use 31 bits, and the last bit is actually reserved for a sign. So that's why we're using 31 bits. And shifting by something in direction where we overflow is just saying, is like the equivalent of taking the first significant bit, which in this example is 0, and just applying that bit 31 times. So we're going to apply it to the entire mask here. So we're going to have 0. Same here. So if we have minus something, we're going to have our first significant bit set to 1. And now we're going to take that bit and apply it 31 times. So we're going to end up with -1. Sorry. And this is how you implement the sign. And this formula is actually going to be used in a couple of places. And it's actually used for like advanced bit manipulations. This 31, this size of int, size of something times the byte size -1 is actually used in a couple of places when you do these sort of advanced bit manipulations. Okay. Sorry. So we have now learned how to create bit masks, or much rather bit sets. We know how to compute the sign. We know a bunch of things. We know how to negate value. Let's do something else now. Let's do a module. And it's not really to do branch elimination, but it's really to be faster because modules is actually really slow. So there's a better way to do it. So let's have our value. Let's do the AND operation, and this is our divisor, and let's subtract 1. So let's do like 34, 32. It worked correctly. There's a catch in this expression though, that the divisor has to be a power of 2. So most of the time, that's fine, we can actually fulfill this requirement, but it's something that you should just know that if you're trying to apply this, you have to have this divisor be the power of 2. And if you have that, if you fulfill that requirement, you're going to have a fast module operation. Okay, so now that we have our like basic building blocks down, we know how to do module, we do know how to do negation, we know how to use certain operations on masks, we know how to compute the sign. Let's actually use all of that knowledge, well, not all of it, but some of it, and let's compute the absolute value. So we're gonna use some of the building blocks that we used before. So we're gonna have a value. We're gonna add that value to a sign. So we're gonna check the sign here, and then we're gonna XOR with a function that actually checks the sign again. And let's see if it works. So for 4, nothing really specific happens. But for -4, we should arrive at 4. And we did. Okay, so what's happening here, right? Because that's much more complicated. And we're using actually 2 functions here. So first is the compute sign. That's the first function. And the second function, which is sort of hidden from view here, is to actually do the unconditional negation. So if it's a positive value, well, there's nothing really to talk about in this example. The interesting bit happens if we have a minus. But let's see what happens if we have like a positive value here. So if we're gonna compute the sign, this is gonna be 0, this is gonna be 0, and this is gonna be 4 XOR with 0, so this is gonna end up at 4. Pretty much simple stuff. Okay. What happens if we have a minus value? This is gonna be this is gonna be -1. This is gonna be -1. All right. So, and this is -4 plus -1. So this is gonna be -5, and it's gonna be XORed with -1. And if you recall what happens if you have XOR minus value X or minus value, we're going to change the sign and decrease the value. So from -5, we're going to end up at 4, and that's correct. So this bit, this whole bit, if you will collapse the signs to -1s, you're going to see that this whole thing actually collapses into negation. Where's that operation? So it is actually this. So it's of course written out differently, but it actually collapses to this. So if we would change the order of the operations, you would see that it's actually equivalent. Okay. So in terms of bit hacks, that's all for this lecture. And if you're interested in how to, like, if you want to know more, I've actually written a article that discusses the same like bit hacks and bit operations, but in much more detail. And there's some more here. So there's source code. There's all of these things that we just talked about, but there's like 0-byte computations as well, so there's just a tiny bit more. So if you're interested, you can check this out. I'm gonna leave the link to this article in the description. If you got something out of this video, leave a thumbs up and leave a like, and possibly maybe subscribe. And yeah, that's all for now. I'm gonna continue doing the bit hacks lectures, because there's lots more to talk about in terms of like probabilistic data structures, performance, branch elimination, what else? Instruction level parallelism, how CPUs works. All of these things are related to being able to do bit operations efficiently. So there's lots more to talk about, and yeah, that's all for now. So thank you. Bye.